This is group A3, and we are talking about Google's algorithm, PageRank. First, let's review the development of page ranking problem. At the very beginning, there's no evaluation. Many searching engines, and even some searching engines for specific information nowadays, do not care the quality of the pages and just return the results in natural or numbering sequences. When there are large numbers of pages to return, there will be a disaster. Then there's an evaluation based on keywords. For example, TF-IDF algorithm. The higher the matching rate is, the better a page is, so is its rank. However, this method may be cheated by a cheating program called term span. And finally, here comes PageRank. Let me introduce its basic ideas on how do we evaluate the importance of a page. In PageRank, it is measured in peer points. How do we calculate it? The peer point of a page equals to, first you divided the peer points of another page by the number of pages that page links to, and then sum them up so that you get the peer point of this page. That means if a page K has 20 peer points and it points to 5 links, so that each page will receive 4 points. But you may ask that you're using peer points to calculate peer points. How do we get started? Well, we use the property of eigenvectors to solve this problem. The peer point of each page is represented by a column vector, and the relationship of pages is represented by a matrix. Aij means the possibility that the jth page links to the ith page. And if the jth page links to the ith page, then it equals 1 over n. If it doesn't, it equals 0. And A is a very special matrix called Markov matrix, such that all engines are non-negative and the sum of each column or row is 1. And it has a special property that it always have an eigenvalue equals 1, so that we are sure to find an eigenvector B corresponding to eigenvalue 1, so that B equals A times B, so that the property of eigenvectors can guarantee the stability of the result. But in real life, we just need to calculate BI equals A times BI minus 1 until the difference between them is very small. I've just introduced its essential ideas, but it needs improvement when it meets different situations. For example, dead ends, which means that a page has no link out. For example, in this situation, D is a dead end. What's the problem? With a row or a column full of 0, the matrix A is no longer a Markov matrix, and the results will be all 0. How do we solve this problem? First, we ignore the columns and rows related to the dead ends. In this example, the matrix A is now a 3 times 3 matrix instead of a 4 times 4 matrix. Then notice that there may appear more dead ends in the process. For example, if we remove D nodes, then now C is a new dead end. We need to move C away. Then we use C formal methods. After that, we backstep. We get the PageRank of a dead end from the PageRanks of non-dead ends. Use this equation. Notice that now the sum of PageRanks is not 1 anymore. The second situation is called spider traps, which means that a set of nodes with no dead ends but no arcs out, which means it only links to itself. It is different from dead ends, for the corresponding row of dead end is full of 0, while that of spider trap node I is full of 0 except AII equals 1. So what's the problem? Once you are out of spider traps, you always have possibility to get in, but once you get in, you never get out of it. So that the PageRanks of such nodes will become larger and larger and finally converge to 1, while the PageRanks of other nodes will converge to 0. How do we solve that? The idea is very simple. We just divide the PageRank of spider trap nodes evenly to all pages with a residential probability, usually set to D equals 0.85. D is estimated from the frequency that an average surfer uses his or her browser's bookmark feature. Thus, Aij is modified to this, and now B is in this form. If we set different values in this column according to the surfer's individual interest, for example, if someone is interested in sports, then we set the entrance in this column corresponding to the pages about sports higher, then the result will be that pages about sports will have better rank. This is especially designed for individual surfers.
Our group write a few programs to introduce about the PageRanks. So let's just make a simple system. There are only 4 webs in the system, and web A has the links to B, C, D, and B have the links to C and A, and C have the links to D, and D have the links to A and B. So what about the PageRank of these 4 webs? We can have a check. So we run the program. It asks whether there are links from web 1 to web 1, and the answer is no. And there's a link from web 1 to web 2, the answer is yes. And I just input this quickly. Yes, we can see here's the links which represent a web to another web, and this matrix represents the links divided by the sum of a web's link. And here's a PageRank of each web, and we can see according to the PageRank, the web 4 is most important, and then 1, 2, 3. So also D is the most important, and then A, B, C. So if we make a larger system, if there are 20 webs in the system, and I randomly input some 0 and 1 which represent the links, and here are 2 special webs. Web 6, it has only 2 links, which is the smallest, and web 14 has the most links to the other webs. So we can have a check about the page rank of these 20 webs, and we can see the most important is web 14 and the number 20 is web 6. So the algorithm of page ranks is quite convictable. And as we said in the previous part, what about we made the problem of dead end, which means that if the web, for example, web 13 has no links to the other webs, we can see the column 13, they're all 0. So if we don't solve it, what about the page ranks of the whole system? We can see the page rank of a whole system tends to become 0. Because I just calculated 70 times, so they're not 0, but actually the whole page rank should be 0. And after we solve this problem, which means that we just separate the special webs separated and calculate the others page rank, and then we calculate this special one, so we can get the proper page rank of each web. And using this system, we can see that first part we don't calculate the page rank of web 13, and then we use these numbers to calculate it, and the page 13 gets its own page rank and has its proper rank of this system. So what about if there some web has links to itself? We made the web 13 has a links which the target is itself. So if we don't solve this problem, what about the page rank of the whole system? We can check, and as we can see, the page 13 got the highest page rank, and the others page rank will tend to become 0. So how can we solve it? And the solution is using the method of smoothing vector. We just decrease the proportion of the main matrix and input another smoothing vector to which will become a part of the page rank of the webs. So we use this system. We can see all the webs have their own page ranks, and the page rank of 13 gets smaller, but we just input the vector is not solve this problem perfectly, because we can see the web 13 is also stay at the number 1. So now we need to use the elements and factors of the interest. If the user have some special interest and all the webs was signed by different fields, so different user will have the different smoothing vectors, and the page rank of all the webs will become different. So that's all about this part.
This clearly, we have an example. Here, we have 4 pages. We take A as ours, B as computers, and the topic of C is computers too. The topic of D is sports. For a topic about computers, S is 0110. And then the formula is modified as this one. This part is about efficiency improvement. PageRank algorithm as the most widely used page ranking algorithm still needs to be improved. Until now, there are lots of methods to polish up it, and it is consummated gradually. Here, we introduce some simple but important ways. The first one is topic-sensitive PageRank. The importance of a PageRank is different to individuals. To take this into consideration, we classify the pages to different topics. Finally, we will get this formula. Here, S, which has a topic, is a vector that if a page is in the topic, the corresponding element is 1. Otherwise, the element is 0. Weight is a small constant. To understand it clearly, we take the second one is sparse matrix. This one is making use of properties of sparse matrix. What is sparse matrix? As we all know, the number of links is very small compared to the scale of the Internet, which means that most of the elements of the matrix are 0. So this matrix is also sparse matrix. If we take that into consideration, we will get this formula, where n is the number of website pages on the Internet. Alpha is a small constant. I is an identity matrix. The third method is weighted PageRank. Weighted PageRank algorithm assigns larger rank values to more important or popular pages. Here, we take weighted in links is the weight of link calculated based on the number of in-links of page U and the number of in-links of all reference pages of page V. We have this formula. Similarly, weight outlinks is the weight of link calculated based on the number of outlinks of page U and the number of outlinks of all reference pages of page V. We get this formula. Finally, we will have this formula. Let's have an example. Here, we want to know the PageRank of page A. In this example, page A has two reference pages, P1 and P2. The inlinks and outlinks of these two pages are IP1 is 2, IP2 is 1. Outlinks P1 is 2. Outlinks P2 is 3. Therefore, weight in links is 2 over 3. Weight outlinks is 2 over 5. PageRank algorithm as a method to sort a big data. It can be used in other sequencing problems. For example, in a large-scale sports competition, we can make use of PageRank algorithm to sort the rank of these teams. We can just regard these teams as pages. This is the end of our presentation about Google's algorithm PageRank.